Welcome to this presentation on a-posteriori Quasi-Monte Carlo error estimation. My name is Marcello Longo and I'm a PhD student at ETH Zurich. I'm presenting this joint work with Josef Dick and my supervisor Christoph Schwab. I would like to thank the organizing committee and the scientific committee of the MC-QMC conference for giving me the opportunity to take part into this online experience. Let's start with the problem formulation. Given a parameter space, the unit cube in S dimensions, so S will denote the number of variables here, and a real valued function on this parameter space, we let Is of f the exact integral of f, and by Q and S of f the corresponding quadrature rule. As customary for Monte Carlo or Quasi-Monte Carlo quadrature, we use uniform weights 1 over n in front of the samples. Now, given a small tolerance tau, our question is how can we choose the number of samples n and a deterministic sampling set Pn such that the integration error is approximately equal to the tolerance. Most importantly, we want to do this without an access to the exact value of the integral, which is in many cases not available. Our question is motivated by several applications. I mentioned here uncertainty quantification of PDE observables. In particular, we want to reduce the computational cost and stop sampling whenever we reach this certain tolerance, and we don't want to train too much, for example, in the case of machine learning, as you see the other application, but also Bayesian inverse problems and many more. The main issue is that all the available bounds for the error are of the following form. So the error is bounded by a constant times a function phi of the number of samples. It's true that for consistent approximation, the function phi tends to 0, but on the other hand, the constant c is not computable. This implies in particular that there is no guarantee that the tolerance is met for any given number of samples. As an example, I give the Cox-Malhak inequality, where the constant c is nothing else than the Hardy-Krause variation of the function f. Then, to answer the question, I outline the talk as follows. First, I'll give an introduction on polynomial lattices and the corresponding function space for the integrand. Then I will explain briefly the Richardson extrapolation and the CBC, so component by component construction of the polynomial lattice rules using extrapolation. And finally, I will dive into the main part of the talk composed of the a-posteriori estimator and some numerical experiments before giving the conclusion. We define now polynomial lattice rules, which are a class of Quasi-Monte Carlo quadrature rules that were introduced by Niederreiter in the early 90s. So we let for a fixed prime number b and a natural number m, this function bm that associates to the Laurent series with coefficients in the Galois field Fb, a number in the unit interval 0, 1. And this is done by truncating the integer part, truncating after the value m, as you see here, and evaluating the function at b. Then the definition of the polynomial lattice point set is given like this. We let an irreducible polynomial p of degree m and a generating vector q with s entries. Then the point set is defined by applying component-wise this function bm to this quotients of polynomials. We see here that the number n, every number n, is identified as a natural number but also as a polynomial. This is given through the natural bijection induced by the b-adic expansion of a natural number. The function space, which is essential for our analysis, is the so-called weighted and anchored Sobolev space. This is the set of smooth functions with S variables with this finite norm. Not all the details of this norm are important. Here I would like to draw your attention to the fact that we have weights in front of the sum, which determine the very importance of each subset of the variables y1 to ys. And for example, for small gammas, for small weights, the variables will be less important. Then each component is derivated at most alpha times. And finally, we observe that this is exactly the same space which is needed for the analysis of interlaced polynomial lattice rules. This in particular ensures that every time we can use interlaced polynomial lattice rules, we can also apply our method. Richardson extrapolation is one of the main ingredients for our study. We have a given approximation QH, parameterized by a small h, of a target Q, such that we have the following asymptotic expansion. Then there exists an accelerated sequence Q alpha approximating Q with these three fundamental properties. First of all, we have higher order convergence, so we only have of h to the power of alpha compared to first order sequence that we had in the beginning. Second, the computation of Q alpha is cheap in the sense that we can compute it by a linear combination of the first order sequence for some specific values of h depending on h star, and the coefficients in front of the linear combination are known, so this a tau are known. In particular, there is no need to evaluate the asymptotic expansion terms, so the C1 to C alpha minus 1. An example of application of Richardson extrapolation is given by the Romberg quadrature, which is nothing else than the extrapolation of the trapezoidal quadrature. In that case, the asymptotic expansion is called also Euler-Maclaurin formula. The fundamental building block and the starting point of our result is proven in a paper by Diggold and Yoshiki, and here I collect some of the main results. Given f in this weighted space and the weights gamma with a certain summability property, then we can construct a polynomial lattice rule such that the Euler-Maclaurin expansion holds, so meaning that we can use extrapolation. Now, existence is of course not enough. We want to know how to construct good choices, Q star and P star. Now, given worst case error B gamma, the component by component construction operates inductively over the dimension. So from D, starting from 2 to S. So first we set the irreducible polynomial P star and the first entry of the generating vector. And then we minimize inductively the worst case error over the dimension computed so far. Now the component by component construction can be also slow unless we use a fast Fourier transform. And this was successfully used also in the case of simpler product weights, which only consist of this part here, but actually this part without the power. But what we do is extending these results to spot weights, which also include this factorial term in front. We see that the construction using fast Fourier transform compares favorably to the construction of interlaced polynomial lattice rules, for example, where instead of having alpha plus s, we had alpha times s. In particular, spot weights enable a lot of applications compared to product weights. For example, forward uncertainty quantification using Carlo-Lev type expansion, random holomorphic nonlinear PDEs, Bayesian inverse problems, shape uncertainties, and many more. Now, first, I give a heuristic interpretation of extrapolation. We know that extrapolation accelerates a first-order sequence, and this is what it is done here. And in particular, it is done by using only quadratures with less points than b to the power of m. So being tau strictly larger than 0, we only use less points, which in particular does not affect the convergence rate of the rule. But on the other hand, we can interpret this sum as a sequence correction of the first order rule. We write this sum as the first order sequence plus some other term, delta q, which is some residual, delta q alpha, and delta q alpha we observe that is approximately equal to the error committed by the first order sequence. To illustrate this fact, I prepared this figure here. We have on the top line the first order sequence again, and in red the convergence point, and on the bottom line you see that how starting from the blue points we construct the orange points, so the second order rule, by adding this quantity delta q. Now, as an example, in the case b and alpha equal 2, this delta q is nothing else than the difference between q to the power of n points and the q computed at 2 to the power n minus 1 points. Moreover, the difference that you see here is composed of high order terms, and this we know because the q2, so the orange points, converge with order 2. In particular, the error, the total error starting from here to here, is dominated by this delta q2 asymptotically. We formalize this observation in this theorem. So for a given set of product weights or also spot weights with a certain summability assumption, we can have this equality. Now on the left hand side we have the exact quadrature error, and on the right hand side we have the a-posteriori estimator. This is of course computable, so we know what is this quantity. And here we have only high order terms, as we've seen before in the illustration. Moreover, the constant here is independent of the dimension. As a corollary, we see that estimator is asymptotically exact, meaning that the efficiency index satisfies this limit. The efficiency index is nothing else than the ratio between the a-posteriori estimator of the error and the exact error. And this converging to 1 means that we can, for moderately large number of points, predict the error almost exactly. Of course, if this would be equal to 1, then we will know the error exactly, which would be the ideal scenario. Now I turn into a numerical example. I integrate over the unit cube. Now I shift the unit cube by 1/2, so I center it at 0 for just notational convenience. And I have here two examples, one using product weights, the separable exponential function, and with spot weights, an affine parametric function, f2. For both functions, we see that this coefficient theta here and here is exactly giving us the summability condition for the theorem. So the eta will control the hypothesis of the theorem. And here we see that in both cases, the relative error and the estimator decay almost in parallel. Actually, it's very difficult to distinguish between the two. And this is both for the case F1 and F2. Just to see it better, I plot also the difference between the two quantities in the plots below. And we see that in the case of product weights, this is the case with order n to the minus 2, so the number of points to the minus 2, which is what is expected by the theorem. While in the case of spot weights, this is in the beginning only order 1, and only after around 1000 points, so only asymptotically, we have higher order convergence. Now, this in particular is important because we use eta equals 2, which is a borderline case. In this case, the hypothesis is fulfilled for product weights, but it's not fulfilled for spot weights. The hypothesis of the theorem, this is what I was talking about. To explain better the importance of these two, of this parameter eta, I prepared another numerical experiment where I fixed the function f2 and I varied the eta. So I first have values strictly less than 2, 1.5 and 1.9, for which we see that the estimator, so here in the circles and the cross, the efficiency index in particular does not converge to 1, because of course the hypothesis is not fulfilled. Nevertheless, we see that it's well within a reasonable range. We are between 0.9 and 1.2, meaning that we can still predict the error with a good accuracy. Naturally, for eta larger than 2, we observe that the efficiency index converges to 1 as n goes to infinity. Here, instead, I fix the eta, so eta is fixed, it will be equal 2.5, while the number of dimension is increasing, so starting from 16 and goes to 128. And you see that the dependence of the efficiency index on the number of dimension is really mild, meaning that we are completely free of the curse of dimensionality. So to conclude, we presented the first a posteriori estimation result for Quasi-Monte Carlo rule that enables a simple algorithm, so a while loop until we reach a tolerance, then we keep increasing the number of samples. And the overhead for the evaluation of this a posteriori estimator delta Q alpha is really little, because the delta Q alpha only depends on previously computed quantities. Moreover, both product and spot weights are available for fast component by component construction, and we are completely free of the curse of dimensionality. Finally, I would like to mention that this can be easily generalized for the a posteriori error estimation of a second or third order rule, actually up to order alpha minus 1. With this, I would like to thank you for your attention and wish you a productive continuation of the MCQMC conference.